We have Einstein's theory of gravity that's already a century old, and we're now living in a time when we are learning more about gravity and how it may appear, actually how it arises from a more microscopic picture. We learned about this by studying black holes, but there are also questions about gravity that we cannot answer easily. I mean, there are problems in cosmology where we see phenomena that we don't fully understand. Like in galaxies, we see that galaxies rotate faster than we would have expected based on the matter that we see. So people try to solve this by adding more matter, like having dark matter. Also, there are questions about the expansion of the universe. It seems like it's expanding in an accelerated way. That tells us that there must be more energy in the universe, a form of dark energy. And our current theories don't explain very well what these things are. I mean, dark matter and dark energy are big problems in our current model. Thinking about gravity as an emergent phenomena by using ideas about entropy and thermodynamics, we are able sort of to derive the gravity equations. And I think that when we start developing that theory further and including the effects of this dark energy, that we can also explain these phenomena that are happening in galaxies. I mean, the current description uses Einstein's equations and extrapolates it backwards, and eventually we have to arrive to this era where we have the Big Bang and everything emerging from, well, very hot, dense beginning. That theory is able to explain a lot of the data, but we like to sort of understand this more fundamentally from this more microscopic way of thinking about gravity and how it emerges. We need to include the effects of quantum mechanics and also the ideas that we have about well, the connection between gravity and the underlying sort of quantum information that's in our universe. Also developments in string theory. So string theory is a theory that tries to combine quantum mechanics and gravity, and actually it succeeded in explaining many things about gravity. In particular, for black holes, there was a prediction, a famous calculation by the late Stephen Hawking, that told us that the entropy of a black hole must be proportional to the horizon area. And in string theory, we have been able to, well, explain this microscopically for particular kinds of black holes, but the general idea sort of suggests that there is an underlying microscopic picture, an explanation of, well, entropy associated to horizons. You have to start from a microscopic theory, and we know the microscopic theory quite well in a universe that's different from ours, namely the one without dark energy, actually with a negative, what's called cosmological constant. But we have to develop this microscopic theory. That's a very big challenge. But then also understanding the steps, how you derive the gravitational equations from that. That's sort of going from the microscopics to the macroscopic behavior of gravity. And then the other thing is then, do we recover Einstein's equations or do we see those deviations? And if it's a difference description, then we also have to develop the correct equations for that. And on top of that, we have to indeed explain then what happens with the evolution of the universe. So how did this new way of gravity, thinking about gravity, how does it change maybe the story about the early universe or the way that matter and structure formed? These are a lot of steps, and I cannot just do this by myself. So one of the other obstacles I'm facing is trying to have other scientists join me in this research and tell them that indeed that we have to address these questions because they're really important ones, but eventually we want to connect it to real observations and solve problems that we have not been able to solve in some other way.